Good afternoon. My name is Nick Samus. I'm with the MITRE Corporation. I'm joined by my colleagues Brandon Bailey from the Aerospace Corporation and Greg Falco from Johns Hopkins University. We're here to talk about some guidance that we've published in a paper for AIAA Ascend 2021 on identifying actionable cyber controls for space mission systems. With that, Brandon's going to get us kicked off with some background.
Yeah, for space systems, there are some policies and procedures out there to help secure those assets and secure the space systems. But what we're really seeing is the lack of the low-level technical detail and the translation we feel is needed for some of these high-level policies and guidances that are out there. We do have some things that are out there from the NIST 853 series or the CNSSI 1253 instruction, and even more recently, the Space Policy Directive 5. So we have some of these high-level concepts and things that are out there, but we feel like there is some low-level technical detail that needs to be derived, and there needs to be a better connection between some of these high-level policy documents and some technical recommendations that focuses on risk mitigation specifically for the spacecraft. There are guidance documents and frameworks out there with NIST and CNSSI that help try to articulate the need to do this for the space vehicle, but the implementation that we're seeing to date in the federal sector is a little concerning. We've seen that we typically see this baseline approach and methodology that applied using the NIST framework or the CNSSI 1253 framework, where it's a low, moderate, high baseline that's provided as a requirement or a mandate. And then when you get into the nuts and bolts of that, if you were to say to a vendor, hey, you need to develop a spacecraft to adhere to the moderate baseline for NIST or CNSSI, you're really just giving them a bunch of things that don't really apply. Like up to 70% of those controls are really not applicable, and a large percentage of those also don't even really help with any type of threat mitigation that we would see. And then on the commercial side, what we see is there's no real adopted standard that's out there. The closest thing we have is the Space Policy Directive 5 that came out in September of 2020. Helps the commercial push the commercial sector in an area where they need to do some basic principles, but it's only high level. Really, it doesn't really dive into some of the really detailed implementations that we feel like are needed for threat mitigation for the space vehicle. So what we do see is occasionally some of the guidance you do see either through SPD5 or for NIST or CNSI that there's bits and pieces that are applicable, but then there's some areas that aren't. And so you can't really take wholesale these things and apply it, the whole thing to a mission. So what we're seeing is some things are applicable, some things aren't, and you really need to kind of come up with these unique baselines and security technical implementations kind of per segment for space, for link, and ground. And some of the uniqueness that space brings is the physical access you lose when it's launched. You need to build right the first time. You have low size, weight, and power, compute, SWaP-C. And you have long development life cycles, sometimes up to 20 years. And then you have this tendency of using quote unquote proven legacy technology, which may have vulnerabilities in it because it has a high reliability, but may have vulnerabilities that could really affect the availability if an exploit happened. So we're gonna hand it over to Greg to talk about the threat model that we're developed.
Thanks, Brendan. Yeah, so in order to run with our study here, we developed a abstracted threat model that's unique to space systems. And so we wanted to look at the difference in the needs to address different threats for both external and internal issues to the space segment. Because when you look at the space vehicle itself, it may be having similar types of attacks against it to other parts of the space system. However, you're going to need to deal with it slightly differently because it is in space and you just don't have that access, as Brandon was talking about earlier. And so we have this abstracted model to help use and organize our guidance on how you would address the different threats to these space systems. And we wanted to look at both the design space as well as the operational space when it comes to space vehicles. And the reason why is because they have very different requirements, and they also have very different needs for addressing threats that are particular to these assets. And so one thing we also want to kind of highlight here is that as you look through the typical processes of identification, protection, and detection for how you would address a space system, the most important part here is they need to support the response and recovery needs of the space asset. Because when you're in space, the only thing that really matters at the end of the day is that mission continues. And because of that, we really need to focus on response and recovery of the asset itself. Everything else that has to do with securing that vehicle should support those needs. And so the way that we began to frame our thinking around this was looking at the NIST CSF functions to inform very specific considerations. Again, looking at the response and recovery components of the NIST CSF first, because right now the way that usually it's framed up is looking at identification, protection, detection, and then there's respond and recover. But because the space vehicle is so critical as that asset, and we're dealing with the size, weight, and power considerations, we need to look at that recovery response element and then go backwards through that NIST CSF function process, looking at this equally different from the design perspective as well as the operational standpoint. Next slide, please. And so the way that we have laid out our plan here for folks to think through these problems is through a decision tree. And the decision tree is really orchestrated to provide a process for designers and operators separately to kind of think through all of the major considerations that they're going to have when improving their space vehicle security. Nick, over to you.
Thanks, Greg. To describe the decision tree a bit, as Greg mentioned, we're really trying to use a requirement derivation process, understanding that response and recovery, having those needs well defined, are absolutely imperative to have before we can actually determine what appropriate protection and detection capabilities we need. The intent here is to be used in an iterative process that we can consider new threats. So not that we understand every single threat today, not intending to provide an exhaustive threat model, as Greg described, but as new threats arrive, we can identify if the capabilities that we have for protection and detection do support effective response or recovery in the face of that new threat. At the end of the day, all of this guidance that we're putting on paper is intended to be used as a starting point, and it must be tailored specific to the organization's unique mission. So as an example here, what we can look at is this table on the left is an extract from one of the tables in the paper. It's identifying high-level needs and challenges that we determined would be important for recovery of a mock system. So in order to support effective recovery, one of the things we identified is to have a high level of certainty that positive control remains within mission operations. In order to do that, what we can then do is identify design considerations or operational considerations for that recovery function. Some underlined text on the right here, the right table here. One of the things we identified is that full command authority of that SV is necessary. Taking that as a core need for recovery can then start that conversation when we talk about response capabilities and ensuring that secondary or failover or tertiary communication channels must need to be blocked in order to ensure that full command authority is coming from an authoritative source. And the intent here is then to move down that stack. Once we identify response procedures appropriately, how do I identify appropriate data sources to detect on? Further, how do I develop a protected enclave so I ensure that the data coming out that I'm detecting on is of high assurance? Again, intent here is to be used through this decision tree as an iterative process so that when we're looking at a single threat or a set of threats, those response and recovery needs are defined commensurate with the threat we're facing. So in applying this guidance, we propose a few things. First, potentially try to define your current cybersecurity posture, your current program capabilities in the vernacular we're using. Try to use the decision tree with an existing use case that is well understood by your organization, may help to identify unaddressed areas. Not going to be an explicit checklist, but will help you identify new questions to ask. If you don't understand a potential area or workflow well, that can help you identify risk where you may not well understand it. The second piece then is tailor these considerations in the tables that we've presented, apply them specifically to your organization's missions. What we're really trying to do here is help provide guidance both across the development and operations within the organization so that we can codify artifacts that's understanding the threats that we're scoping our system to. We can identify the gaps in our current capabilities in order to find requirements for target future state. And over time, iterate on this process to define well understood knowledge on how our space systems do operate and can operate in the face of adversary. With that, we thank you for your time.